All right, we've talked about empirical formulas before, but now instead of you given the empirical formula for a compound, you will determine the empirical formula. So if you recall, an empirical formula is the simplest formula in which atoms combine in a compound. It shows the smallest ratio of atoms in that compound, and it may or may not be the actual formula of the compound. So just again for comparison, let's say a chemical compound has a molecular formula of C2H6, what would its empirical formula be? So we have an actual ratio of 2 to 6. We can simplify that and get a ratio of 1 to 3. Or another example, if a compound has a molecular formula C6H6, a 6 to 6 ratio of carbons to hydrogens, the simplest or smallest ratio would be 1 to 1. So before we get into determining empirical formulas, let's talk about what these subscripts in a chemical formula represent. And we'll use water as an example. So water is the chemical formula H2O. So what do the subscripts tell us about that compound? Sure, it tells us that there are 2 hydrogen atoms for every 1 oxygen atom in 1 molecule of water, but we want to look beyond that. So what if we had, say, a dozen water molecules? Now be careful with how I'm going to ask this question. Make sure you're careful, rather, how you answer it. Let's say we had a dozen water molecules. In a dozen water molecules, how many dozen hydrogen atoms are there? Pause the video if you need to. In a dozen water molecules, how many dozen hydrogen atoms are there? There would be 2 dozen. You can count them. Or in a dozen water molecules, how many dozens of oxygen atoms would you have? You would have 1 dozen. Well, we don't deal with dozens in this class. Instead, we deal with things called moles. So what if you had a mole of water molecules? How many moles of hydrogen atoms would you have? You would have 2 moles of hydrogen atoms. And in a mole of water molecules, how many moles of oxygen atoms would you have? You would have 1 mole of oxygen atoms. So what that means is that in the chemical formula for a compound, these subscripts represent a mole ratio. 2 moles of hydrogen for every 1 mole of oxygen in a mole of that compound. So that's what we're going to look to do when we determine empirical formulas. We want to find the mole ratio of atoms in the compound, and that ratio will simply turn into our subscripts in the empirical formula. With all of the problems that we will be doing in this class, you're going to be given one of 2 things. You will be given either 1, the mass of each element in the compound, or 2, the percentage composition of that compound. So given either one of those, mass of each element in the compound or percent by mass of each element in the compound, we can use that information to determine the empirical formula. Let's take a look at some examples. The compound contains 14.0 grams of nitrogen and 32.0 grams of oxygen. What is the empirical formula of this compound? Now again, remember what these subscripts in the empirical formula represent. They represent a ratio of moles. Well, we don't have moles. We're given the mass of each element in the compound. So our first step is to take those masses and convert to moles. So here's our setup. So again, to convert from grams of a substance to moles of a substance, we're going to use molar mass. Now a common mistake here is to use Hofbrinkel. So we're not trying to find moles of nitrogen molecules. N2 is a molecule. Nor are we trying to find moles of oxygen molecules. A molecule of oxygen is O2. We're trying to find moles of atoms, each atom in the compound. So 1 mole of nitrogen has a mass in grams of about 14. And likewise, 1 mole of oxygen atoms has a mass of 16. Now, I know you can do this math in your head, but I do need to see this work. So you got to show me the work. And then if you want to calculate in your head, that's fine. Just don't mess up. Most often, you won't be able to do the math in your head. So let's go ahead and give these values to 3 sig figs, since the quantity we started off with has 3 sig figs. and our molar mass also has 3 sig figs. So once again, our numbers are really easy to work with, but I still need to see this next step. Here's our next step. Once we find the moles of each atom in the compound, we're going to take the bigger number of moles and divide that by the smallest. We always do bigger divided by smaller. So let's set it up. Make sure you label correctly. I almost messed up there, so you want to keep track of what's what. And so when you take the bigger number of moles and divide it by the smaller number of moles, I want you to express the answer you get on your calculator as a ratio, a different way of writing a ratio. Not a this over that ratio, but a this dot dot that ratio. So here's what we get. So in this compound, there are 2 oxygens for every 1 nitrogen. And our last step is then to take that ratio and turn it into subscripts in our empirical formula. So now what goes first, nitrogen or oxygen? We learned that the more metallic or less electronegative element goes first, which in this case is nitrogen. Or a lot of times we put them in order that they're given to us in the problem. That's not always the case, and I'll tell you when it's not the case. But I'll try to make it so that the first thing given to you in the problem is the first one in the formula. Like in this problem, the mass of nitrogen was given first, so we're going to put that first. So according to our ratio, how many nitrogens are in the empirical formula? Just 1. According to our ratio, how many oxygens are in the empirical formula? That would be 2. So our empirical formula of this compound is NO2. All right, I'll let you try one. Same process. Says a compound contains 2.00 grams of carbon and 5.33 grams of oxygen. What is the empirical formula of this compound? So set it up the same way that I did the previous one. Take the mass of each of those elements and convert to moles. Divide the bigger number of moles by the smaller number of moles to get your mole ratio. And lastly, your mole ratio becomes the subscripts in your empirical formula. All right, go ahead and pause the video and work that out. So here's our setup. We get 0.167 moles of carbon, 0.33 moles of oxygen. Take the bigger number of moles divided by the smaller. We get, again, it works out really nicely. Your ratio should be very close to a whole number. Sometimes it's not. I'll show you what to do in that instance. But in this case it is. We get a nice whole number ratio, 2 oxygens. Again, that's not 20, that's 2 oxygens. For every 1 carbon, carbon goes first. And so we get an empirical formula of CO2. All right, let's take a look at the next one. It says find the empirical formula of a compound that has a percentage composition. So this time we're given the percent. Again, this is percent by mass of each element in the compound. 48.7% fluorine and 51.3% calcium. Again, it's important to understand that these are percents by mass. So let's do this. Anytime you're given the percentage composition of a compound and we're trying to find the empirical formula, we're going to make an assumption. Let's do this. Let's assume you have 100 grams of this compound. Now, if you have 100 grams of this compound, of that 100 grams, how many grams of it would be fluorine? Well, since 48.7% of the compound's mass comes from fluorine, if you had 100 grams of the compound, you would have 48.7 grams. And in 100 grams of this compound, of that 100 grams, how many grams would be calcium? That would be 51.3 grams. So now we're at the same place we were in the previous problems. Now we have the mass of each element in the compound. So just that one additional step there in the beginning. You can assume any amount, but 100 works out nicely. If you have 100 grams of the compound, then those percentages just turn to grams, and the rest is the same from there. So I'll let you finish this problem. Go ahead and determine the empirical formula. This one, though, calcium, even though it's given to us second in the problem, goes first in the empirical formula. Go ahead and pause, see what you get. So here's our setup. A couple things to notice, as opposed to the very first problem, I didn't put moles in our ratio here, so I got 2.56 F over 1.28 Ca. At least make sure you label the substances. It's really easy to get your ratio backwards if you don't label. So just label it like that. So again, we get, it's not always 2 to 1, but we get a 2 to 1 ratio of fluorines to calciums. So the empirical formula of this compound is CaF2. Now, let's try one more, very similar to this. I'm going to let you set it up all the way. Except for this one, I want you to stop at the ratio. Don't determine the empirical formula. Get your moles, divide your moles, and get your ratio. There's something that's a little bit different on this one that I want to show you how to finish. So go ahead and pause the video. Get just to the mole ratio. Get that ratio and stop there. So this time we get a 2.5 to 1 ratio. Question for you. Is that 0.5 close enough? Is this 2.5 close enough to round up to 3? Do we get a 3 to 1 ratio? The answer is no. Is it close enough to round down to a 2 to 1 ratio? The answer is no. If we're going to round a ratio, it's got to be really, really, really close to a whole number ratio. So 2.97 to 1 or 3.05 to 1. Those would round to 3 to 1. But in this case, it's too far to round that. So this time, instead of rounding to a whole number ratio, we're going to multiply to make it a whole number ratio. So what can we multiply by to make that, instead of a decimal ratio, a whole number ratio? In this case, we're going to multiply by 2. Now don't forget to multiply both by 2. So instead of a 2.5 to 1 ratio, we get a 5 to 2 ratio. Phosphorus goes first in the empirical formula. And we end up with an empirical formula of P2O5. Now, what are some other decimal ratios that we would need to multiply? Well, what if you have a 2.33 to 1 ratio? Is that close enough to round down to 2 to 1? Nope. In that case, we're going to multiply by 3. Or what if we had a 2.25 to 1 ratio? This time we're going to multiply by 4. What if we had a 2.20 to 1 ratio, or just a 2.2 to 1 ratio? That time we're going to multiply by 5. And what if we have a 2.67 to 1 ratio? We're not going to multiply by 6. Start with times 2. If that doesn't work, go to times 3. If that doesn't work, go to times 4. Keep going until you get really close to a whole number. So 2.67 times 3 gets you really close to a whole number. So if you got a something 0.67 to 1 ratio, we're going to multiply by 3 to make that a whole number ratio. All right, go ahead and pause the video and give this one a shot. Get the empirical formula. Go all the way. So this time we get a 1.33 to 1 ratio. So we're going to multiply by 3 to turn this into a 4 to 3 ratio. 10 goes first in the empirical formula. So we got SN3, N4. All right, let's try a little different one. You have 10.00 grams of propane, which is a compound known to contain the elements carbon and hydrogen only. And it was analyzed and found to contain 1.84 grams of hydrogen. What is the empirical formula of propane? Well, we're given the mass of this whole compound, 10.00 grams. But we're only given the mass of one of the elements in the compound, 1.84 grams. So be careful. The tendency is to use the 10 grams and think that that is grams of carbon. That is not grams of carbon. That's grams of carbon and hydrogen. So we need to find the mass of the carbon in this hydrocarbon. And again, if you do this just on your calculator, you're going to lose points. So make sure you show the work. So we'll subtract the mass of hydrogen from the mass of the whole compound, and that will give us the mass of just carbon. Go ahead and do that. Now that we know the mass of each element in that compound, we can take those and convert them into moles. Find a ratio, get the empirical formula. Go ahead and pause the video and finish this problem. So we get a ratio of 2.67 hydrogens for every 1 carbon. Not close enough to round up to 3 to 1, so we're going to multiply by 3 to turn that into an 8 to 3 ratio. And so carbon goes first, always in the formula of a hydrocarbon or any compound that contains just carbon and hydrogen. And so we get C3H8. Now let's do one more, a little different problem. I know there's not room for it in your notes, so go to the back page of your notes and let's try this one out. Go ahead and pause the video while you copy the problem. I'll read it to you first. A compound consists of 32.4% sodium, 22.6% sulfur, and 45.0% oxygen by mass. What is the empirical formula? So notice this one is a little different than the others we've done because this compound has 3 elements in it. So go ahead and pause, write it down, and I'll walk you through it. All right, so our approach is the same. We're going to make an assumption. We're going to assume you have 100 grams of this compound. And so that means we have 32.4 grams of sodium, 22.6 grams of sulfur, and 45.0 grams of oxygen. So go ahead, convert those to moles, and then stop there. I'll show you how to proceed, and then I'll let you finish it. Go ahead and pause the video. Stop at moles. So here we have moles of each of the elements in the compound. Notice we have 3 moles. We have 3 elements in this compound. So think back. If you have a compound that consists of 2 elements, how many ratios do you need to get the empirical formula? You just need 1 ratio. Your book is also going to show, by the way, the smaller number of moles divided by that same number to get a 1. You don't need to do that. How about here? If you have a compound that consists of 3 elements, how many ratios do you need to determine the empirical formula? That answer is 2. So how are we going to do this? There's a number of ways of doing this, but there's one, what I feel, really good way of doing it. Here's how it works. Make sure to divide 2 of them by the same thing. So in this case, you're going to take the 2 bigger number of moles and divide each of them by the smallest. Always divide by the smallest, and make sure you divide the 2 others by just the same one. So always divide by the same thing. So let's set that up. So here are our 2 ratios. We have 2 sodiums for every 1 sulfur, and we have 4 oxygens for every 1 sulfur. Again, it's important that we divide both the sodium and the oxygen by sulfur. And if we do that, then the sulfurs in our 2 ratios are going to be the same. If they're not the same, though, make them the same. So what is the order of the elements in this compound? I'll make sure with these ones that I give you the elements in the order that they appear in the formula. So we have N, A, S, and then O. So according to the ratio, how many sodiums in the empirical formula? According to the ratios, both of them, how many sulfurs in the compound? And according to the ratio, how many oxygens in the compound? So our empirical formula is Na2SO4. Of course, that is the formula for sodium sulfate. All right, we'll stop there. Make sure to do lots of practice so you can get good at this. Next, just a preview ahead, we're going to be learning about how to determine the molecular formula of a compound. We've done this before, but it's a little more work now that we know how to determine empirical formula. Thanks for watching.